All right, so today we're going to more formally start talking about functions. Just remember that there's no class and there's no live stream on Friday because of the home game. And then Friday after that, the 27th, is your first exam. Next week is your Fix-It week, where you can resubmit one hack and one lab, and then also work towards studying for that exam on that Friday. More details will, of course, be posted in CampusWire later on. But otherwise, we already saw functions to a certain extent when I previewed them over here, that we realized that if we're going to round descents more than once, maybe we should put that into a function so that we can reuse that code over and over again. Monthly payment, that required, a pretty substantial amount of computation there. And I don't want 4 lines of code stuck, even if I'm only going to do it once, I don't want 4 lines of code stuck in the middle of my program when I can put that off to one function and keep, isolate all of the logic to do that over there in that one function. So what we're going to do now is we're going to talk about these functions in a little bit more detail. A function is, more formally, a reusable unit of code that may take inputs, more than one input is possible, and may produce an output. It doesn't have to produce an output. And it's similar to math functions, right? If I were to write the math function f of x is equal to x squared, once that's in full math mode there, then what's the input? The input to this function is x. When you evaluate it, if I put in 2 for this function, then I'll get out 4, right? We call that y, right? Y is the output. So in this particular case, x is the input, a single value, and then y ends up being the output. Right? That's what we look for with respect to math functions. The name of the function, the name of the function is f. Why? Because mathematicians don't have imaginations. What is this function doing? It's just a function, so I'll call it f, right? Or what comes next? G. What comes next? H. So a lot of their functions are called f, g, and h because they start out with function. Our functions do things. Our functions do things like round to cents or get you the monthly payment. And so our functions will be named something that is clear and descriptive of what they actually do. With math functions, you can, of course, have multiple inputs, right? There could be one input. You could have f of x, y, which has 2 inputs. You could have f of x, y, z, right? That has 3 inputs. You can also have input in math. You can have a function with no inputs at all, right? Something like that. In math, what kind of function would you be looking at there? No inputs. It doesn't matter what the input is. The output is always the same. Say 5. It's what? A constant, right? It's a horizontal line, all right? Just like math, a function can only ever return at most one thing. Right? Otherwise, it wouldn't be a function. The typical example that math folks will give you is the circle. Is the circle a function? No, why? What is that thing, that test that you can apply to say, nope, this is not a function? The vertical line test. You draw a vertical line across that circle, and it intersects at 2 points. That's because there's one x value that is mapping to 1 point above and 1 point below. You can't have that. You can only ever have one return value, one value that is the output. We've already seen plenty of functions in the math library, right? Sine, square root, pow. We've also seen functions in other libraries. Printf is a function, right? It does something. Main, the functions that you've been writing, that is a function. The reason that we like functions is because it facilitates code reuse, right? Code reuse. I don't want to have to write that same multiply by 100, divide by 100, and call round over and over and over again. I want to put that into one function and reuse that code. You don't have to copy pasta the same code over and over again, right? And to get the same results. Instead, you can put it into a function and simply reuse that function. It also goes along with the dry principle. Does anybody know what the dry principle is? No, it's not DRY. It's not. It is DRY. It's not DIY. Is what I was thinking. It's not do it yourself. The DRY principle is don't repeat yourself. Right? Don't reinvent the wheel. Don't roll your own. If you can, you put it into a function so that you're not repeating yourself. It also works into something called procedural abstraction. These are all reasons why we would want to use functions and write functions. And to motivate this, I'm just going to ask you a question. How does the square root function work? How does it get a square root out of that? Or just take your calculator and there's a square root button on it. How does that button work? Right? Have you ever thought about that? No? If you have never thought about that, great. Why haven't you thought about it? It just works, right? And that's what procedural abstraction is. Who cares how it works? You just want the functionality. You just want to be able to compute the square root. So now, if you had to write the square root function, then you need to care about how it works. But if you just wanted to use that functionality, all you need to do is use it because somebody else wrote a function for you. It abstracts away those details so that you don't have to worry about them. There are actually dozens of different ways of computing a square root. There's a scale and interpolation method. There are other interpolation methods. There are Taylor series. I could name it maybe a half a dozen things if I looked them up on how to compute the square root function. Which one does it do? I don't care. It just does it, right? It reduces our cognitive load. We don't have to think about it, right? We don't have to think about those lower level details. I'm trying to solve some other problem here. I'm trying to find the roots of a quadratic equation. I don't want to have to worry about the details of computing a square root to see what those roots are, right? It reduces our cognitive load and it reduces everybody else's cognitive loads. The details are encapsulated inside the function, and we don't have to worry about it, right, anymore, unless we, of course, have to write the function. But once we've written the function, then we never have to worry about it again, right? And it feeds into an overall design principle with respect to problem solving, right? What's the first question that you ask yourself when you approach a problem? So when faced with a problem, what is the first question you should ask? Right? So what's the first question you would ask? Let me give you some motivation. Why do we like programming to begin with? It automates things, right? It takes work away from us, grunt work away from us so that we don't have to do it anymore, right? So put yourself in a lazy mindset. I don't want to have to work, right? So now I'm faced with this new problem. What's the first question you should ask yourself? What is the problem? Understand the problem, but again, be lazy about it. I don't want to have to work. I don't want to have to solve this problem. How can I make this easier? By getting somebody else to do it, right? Is it already solved? In other words, does a function already exist for me to use, right? Or can I adapt a function in order to solve this problem, right? For example, square root, I need to compute the square root. Somebody's already solved that for me. I'm good to go. I'll just call their function. But we asked ourselves a question of how do I round a sentence? Okay, well, I don't want to have to work too hard. So what I'm going to do is I'm going to use an off-the-shelf solution, the round function that's already written for me in the math library, and I will adapt it by moving that decimal place over a little bit, calling that function, and then moving that decimal place back a little bit. Right? In other words, I've adapted this function to do something that it didn't do before, and I've solved that problem with doing half the work. And by the way, actually doing a correct round function can be actually kind of difficult because you've got a whole bunch of corner cases to think about, right? But otherwise, I'm going to reuse that, right? And it goes again into not just laziness, but you can never hope to match all of the hours, days, weeks, whatever of work that have gone into developing these libraries. The standard libraries, they're dozens of years old, right? They have been tested, right, millions of times. They have been debugged. They have been optimized, right? You will never hope to match those thousands and thousands of hours that other people have put into it if you don't have to, right? External libraries are also an option. Right? Later on, we'll be using external libraries, for example, to process images in the next couple of weeks. right? No, I did not write any code to process an image. Instead, I brought in an external library to do it. And then I wrote wrapper code to make it easier to interact with that image so that you can flip the image or rotate the image or doing something like that. Right? External libraries. And it's only possible if you can write and use functions. Right? So let's review what we did yesterday or Monday with respect to our functions. As with variables in C, you have to declare functions before they can be used. In C, you declare a function by writing a prototype. Right? So what is a prototype? A prototype is a function signature followed by a semicolon. Right? So let's jump up here. There's the prototype for round descents. Right? There are three components to this. Remember, we're not mathematicians. We're not going to name our functions f, g, and h. We're going to name them what they do. The name of the function is round descents. This is a value type that it returns. This is its inputs. Down here, we've got another function with a different name, same return type, but three inputs. One of them is a double, the second one is a double, and the third one is an integer. That's what a function prototype is, those three things. So a function prototype is the name or identifier of the function, right? The return type of the function, right? That is the type of variable it returns, right? And or outputs, and finally the inputs, which are called parameters, arguments, or inputs. Right? We'll probably go with parameters here as the most common term for these. Okay. Again, you can have a function with 0 parameters, no input. That's a constant function. It does the same thing every time you call it. You can have a function with 1 input, just like f of x, 2, 3, 4, 5, 7 inputs if you want to. Okay. After you have created that prototype, you can actually use that function. Again, this example. I declared that there's this function called round descents that takes a double and returns a double. But I didn't actually say what it does yet. I do that down here at the bottom. But I can still use it. I use it here on line 35. I use it here on line 40 and line 41, right? And up to this point, up to line number 41, I have not said what that function does yet. That's where these definitions come in, right? So once you have that function, you can actually use it. But the prototype does not define what the function actually does. Instead, later, you provide a function definition, right? What the function does. When you do that, you repeat the signature, but instead of a semicolon, you provide a function body, right, within those brackets, opening and closing brackets. Right? Every time you call that function, the code inside that function body is executed. Every time you call or invoke that function, the code inside that body executes. Right? I called that round descents function 3 times. What happens is when the first time I call it on line 35 right here, what happens is that control flow is interrupted. It's not going to go on to line 36 until this function has executed. So control is turned over to round descents. It executes the code within that body. And then eventually when you get to a return statement, it returns back to where you came from, up here at the top at line 35. Then it continues with the normal control flow down here. Okay? All right. So some other observations here. Actually, no. Okay. Yep. There we go. The function body computes the result and returns it to the calling function, i.e. using the return keyword there. So some observations here. Again, you should always, in fact, we grade on it, use doc style comments on the function prototype. Right? And remember the DRY principle, DRY. Documentation should not be duplicated on the function definitions, right? So what if I had taken this documentation, copied and pasted it down here, and put it on the definition again, right? Now I've got two copies of the same documentation. What happens when I go and change one of them? Now I've got to change two of them. DRY, don't repeat yourself. Don't put two documentations down when one will suffice, right, up here. But you should have doc style comments. Remember that doc style comments are going to be /*, a vertical line of stars, along with whatever you need to put in there, and then a slash at the end there. All of those stars should be aligned like that. If, let me go ahead and copy this so I don't lose it. If you start typing it directly like that and just hit enter, it'll automatically do the formatting for you. Right? And you note here that it appears in green. If I had a single, I guess that's also green. Hello, right? That's also green. In some IDEs, the doc style comments will have a different color because it's actual it realizes that this is intended as documentation. Apparently not here though. Okay. All right. So documentation should only be there once, right? On every prototype. Another observation here is about scoping. Right? Any variable declared inside of a function is local to that function and only exists inside that function, not outside that function or any other function. We did that with respect to the get monthly payment. Let me come down here. I declared 1, 2, 3 variables that are all local to this function. Months, which is years times 12. That is not the same months as this months up here. There are two different variables called months. There's one on line 34 that's inside the main. There is one on line 57 that is in a completely different function. They have the same name, but different scopes, and so they can live harmoniously together in different scopes. If I change one, it has no effect on the other, right? And vice versa. All right, we'll talk about how that works in more detail probably after, or probably next week. But otherwise, let's start talking about, let's see, yeah. Let's start talking about how to separate these things properly. The way that I did it over here is I just put this all into one big giant file. Right? Now, that's okay because our program is only, 60 lines of code? Most programs are not this small. Most programs are going to be thousands of lines of code, hundreds of thousands or millions of lines of code. Right? We call those locks, lines of code. Right? Generally, fewer locks are going to be better, right? Because it's more succinct code. But even the more complex of a project, the more complex of a system, you're going to have millions of lines of code. It's probably kind of old, but I think the space shuttle that's no longer used, their software was something like in the order of 100 million lines of code or something, right? Something like that. I don't know. You can look it up and find out how many lines of code there are. But even in a simple database system, there are going to be millions of lines of code. Right? So is it a good idea to put that all in one big giant file? 100 million lines of code in one file. Lots of problems. First of all, there's no organization. Second of all, you are editing this one big giant file. Good luck with that. That's going to be gigabytes of data that's open in your editor at a time. Third of all, you're going to be working on a team, right? Where there are hundreds of people that are working on the same code base. 100 people editing a 100 million line file, right? Everybody's going to start stepping on each other's toes at some point. There are going to be huge merge conflicts, right? When you try to come together and decide on which lines to keep and which lines to not keep. So what I want to do is I want to start coding modularly, right? What you want to do is you want to separate utility functions into their own files. Right? The prototypes will and documentation will be placed in a header file. Right? That is with a .h extension. That sounds familiar. Where have we seen .h file references before? Yeah. Libraries. We're making our own library now. Right? The standard input .h file, the header file for the standard input output library. The header file for the standard Boolean library. The header file for the math library. Right? The definitions will be placed somewhere else. The definitions are placed in a source file with the same base name plus .ac. All right. So let's do an actual demonstration here. All right. What we're going to do is we're going to separate our financial utilities functions into a separate library. All right. I'm going to call it financial utils. Financial utils. All right. .h. The naming convention here is old school C, where everything is lower camel cased and then an underscore there and a .h. Again, this will contain our prototypes and our documentation. And then I'm going to put the source file, financialutils.c. I'm going to put the definitions over in that file. All right. So let's go ahead and do that. I've got my basic loan program here, but now I'm going to go ahead and create a financialutils.h. Right. Sorry, I have to always phonetically sound something out in order to spell it correctly, or like that. Otherwise, financialutils.c. There we go. All right. So the first thing I'm going to do, I'm going to get rid of that demo file there first. I'm going to take the prototypes and the documentation, and I'm going to move them off over here into this file. All right. Saved file. Then I'm going to take the definitions and place them into another file. The source file there. All right. Now this is a multi-step process. Do you see a main over here in this financialutils.c anymore? Nope. It's not an executable file. It is now a library file. I can compile this, but I can't get a runnable file out of it, just like the math library does not run, right? There is no main in the math library. There is no main in the standard Boolean library. Those are utility functions that you can use. Right? You can use the square root function. You can use the sine function, but there is no main function over here. There is only ever one main function for an executable program. Right? The second observation that I'm going to make here is, did I declare my functions before I define them? So remember, in C, right? As with variables, functions in C have to be declared before they can be used. So did I declare the prototypes here at all in this file? Nope. I did that over here. Right? So the solution is going to be to include that other file, financialutils.h. Just like we did with the math library, the standard input-output library, the standard Boolean library, etc. Now, I'm using double quotes here instead. Right? The double quotes are different than the Langle. We call these Langle-Wrangle, left angle bracket and right angle bracket. So Langle-Wrangle, right? So left angle bracket, right angle bracket, right? Those things right there. Right? You do that with standard libraries, right? With user-defined libraries, you use double quotes, right? So let's note that down as well. So in the .c file, I will add and include financialutils.h to include the prototypes, right? Use double quotes for user-defined libraries, right? Langle-Wrangle for the standard libraries, right? And there, now I can go ahead and compile this thing. Right? GCC financialutils.c. This is not going to work. It's going to complain about a lot of stuff, first of all. It's going to complain that you didn't link in the math library. All right, fine, I can do that. Oh, good, okay. I skipped something, sorry. I am using math stuff here, right? I'm using a math thing there, I'm using a math thing there. So what else do I need to include? The math library. Include math.h. There we go. Am I using any standard input-output stuff? I don't see any printfs here. Am I using any... I could include the stdlib. That's automatic though, but you can go ahead and include that. Am I using anything else? Standard Boolean library? Nope. So only include the libraries that you need to, and then include your own header file here. Now that should clean that up a little bit. In fact, I don't need to link in at all. I guess I do. Fine. LM. There. It's still not compiling because it thinks you need a main. You want to create an a.out, an executable file, right? Then I need a main because I need to know where to start. But I don't see any main here at all. Right? To solve that problem, we're not going to create an a.out file. What we're going to do is something that we did on the second day or maybe the first day or something in the demo, right? Where I use this -c flag, financialutils.c. That -c flag stands for compile, but do not create an executable file. Over here, if I were to refresh that, do you see what's now been added? That out file, that .o file. That stands for object, right? That's the actual code. Of course, we can't open it up because it's a bunch of machine code, right? But that's what we can use later on to compile the entire loan program. All right, let's go ahead and compile the entire loan program now. The problem here is that I've removed those utility functions and put them over here into separate files. So the first step is to bring those in as a new library. Include financialutils.h. Right? And now it at least has the prototypes. Right? I'm going to get different warnings now. There we go. All right. I understand that there are these functions out there called round to cents and get monthly payment, and I see that you're using them down there, but when I go to try to create an a.out file, I can't find them. Right? So now we need to tell it where to find them. Financialutils.o. That's where you can find them in that object file. Right? Loan.c. Right? And then, I guess, lm. lm, there we go. Right? There. So all again together. Go ahead and compile with that object file, compile that C file that actually has the main function in it, and make sure to link in the math library to find that other math.o file somewhere on the system. And I can run this the same loan program as before. All right. So again, the step-by-step process here. In our main, and I'm putting that in double quotes there, not the main function, but in the main source file, loan.c, then what you do is you include the financial utils.h file, right? And then to compile, what we do is a series of compilations. So gcc -c financialutils.c, right? Which compiles the library into an object file, financialutils.o, right? And then compile compile all together. GCC financialutils.o loan.c and then -lm to bring in the math library. Right? And let me make this look a little bit better. I think there we go. That looks a little bit better, at least, because I can include there. It'll render correctly on GitHub when I push it out there. All right. So there's your primer on creating your own libraries. Libraries generally should be small, right? These are financial utils. Should I put something like a, I don't know, user password reset function in a financial utils? Now that probably belongs over in some other library. If you've got math stuff belongs in the math library, financial stuff belongs in the financial library, input-output stuff belongs in the input-output library. You put stuff into libraries that make sense to organize code. And now you don't have one big giant file, right? Some files are still going to be hundreds of lines of code, but certainly not millions of lines of code, right? This can get quite quite complex with many different source files, source and header files. This can get very complex, right? In fact, the solution would be to use a build system like make. Right. So that's an entirely different language. You'll get exposure to this after the first exam, where we give you make files, because we're going to give you maybe half a dozen different source files. In this make what's called a make file, we put down all the rules for building stuff, because this one has a dependency on that one, so that one has to be built before this one can be built. This is how you build that thing, and this is how you build that thing, and a whole bunch of different rules. You could have make files that are hundreds or thousands of lines of make file code, completely different language, that is just responsible for building your program. Not any of the code in your program. It's just responsible for actually compiling and building your program. In fact, there are entire jobs like that out there. They're called DevOps, if you've ever heard of that term, development operations. They don't write any code. They write the code to manage your code. Because if code gets in very complex, millions and millions of lines, you need maybe one or two or three, an entire team of people to manage all that code. They never write any of it. They never test any of it. They just write the code that manages it, right? So there are entire jobs that you can have to do this kind of stuff. All right. Let's see. Okay. Yeah, we can do this as an end part. Now that we've got a unit of code, right, remember that the definition of a function is a reusable unit of code. Now that we have the notion of what a unit is, we can start doing unit testing, where we've got this piece of code and we want to make sure that it's a correct piece of code. Right? A unit is a piece of code, usually a function, that can be tested. A unit is an indivisible piece of code that we treat like a black box. We say it's a black box because you can't see inside of it. You're not allowed to open it up and look at its insides. Instead, you have to treat it like a black box, where you feed it inputs and it gives you an output, which is exactly what a function is. And we want to test that in isolation. We don't want to call that function and that function and that function and that function, and all these things have interdependencies. We want to test this one piece, because then once we know that this one piece works, then we can start wrapping it around in other pieces to test those pieces. Right? So what is a unit test? Kind of like what you've been doing with CodePost. A unit test is an input-output pair, right, that is known to be correct. Right? It is determined to be correct before you write your code. And this is why we've been directing you to understand the problem by coming up with a few test cases yourself. The air distance or something, where you come up with, I don't know, a latitude, longitude for Lincoln and a latitude, longitude for Omaha, and then you put it into your calculator and you come out with it's like 50 miles between them, or whatever that is in kilometers, right? 80 kilometers away. And there is your input-output pair. Or you go to Wolfram Alpha and you ask it, what for this input to this function, what would I get? It gives you an input-output pair. Right? It's either something that you've determined yourself by hand or by some other tool to be correct. Right? We unit test by feeding our known input, correct input, to the function. Oops, sorry. By feeding the input into our function, our unit, right? And comparing the result to the known correct output. This is the actual output versus the expected output. The expected is what we determined when we created the input-output pair. The actual output is what your program produces, right? And it passes if they match. It fails if they do not match. I'm going to put match up there in quotation marks for a second there, because we're going to be okay with like close enough or something, right? So grouping multiple units together forms what is called a test suite. And that's exactly what we do on CodePost. We come up with test cases that we pre-computed, this is the correct result. And we write code to search your output for the expected output. And then if it fails, down at the bottom, we give an error message, your output does not seem to contain the following line, right? But we also have to be a little bit, fuzzy about it. For example, on the air distance, I believe, we put in that if you were within like 0.001 of the expected output, we passed it. So if you were off by, a millionth or something, it was fine. It was close enough. That's why I put match up here. What does it mean to match? Right? So matching criteria. Matching criteria, right? For integers, an exact match is needed, right? So for example, you use equals equals, right? If I expect that the output is 5 and you give me 4, no, that's way too far off, maybe, right? There are some use cases where maybe that's close enough. For floats, floating, or for doubles, it may be okay to be close enough, right? In other words, within point, I don't know, 0.00001 of each other, and that's where a delta comes in, right? If you're within, what is that going to be? Tenths, hundredths, thousandth, 10,000th, 100,000th. If you're within 100,000th of the actual value, we'll go ahead and pass it, right? All right. So if a future bug is reported, you have a new test case, right? Why? Because a user says, oh, it didn't give me the expected results that I expected. Okay, well, what did you input to it? All right, what did you expect? All right, there you go. There's a new input. And when you go back to your code and you write that as a test case, yeah, it fails because my output is off. That gives you a hint as to how to go and debug your code. What happens when I give it that input? You trace through your code and you find, okay, there, that's the line that screws up there because that's giving me the wrong result there. When a future bug is reported, then you have a new test case, right? And tests should be repeatable, right? That I don't want. If you have a new bug that's reported, but you had like 10 different test cases that all passed, and now the 11th one is not passing, right? Then you need to be able to write that new test case, fix your code, and rerun all 11 of those test cases in your test suite very, very easily. It's not going to be, I'm going to run this manually for this input. Okay, that checks off. Check it off on a piece of paper. Run it on this input. Yep, that check it off, and do that manually, right? We don't like manual work, right? So they should be repeatable, i.e. automated, right? Not manually checked or tested, right? For that reason, you need to write code to run your test cases. Right? And we can do that pretty easily. Let me come over here and I'm going to create a new file. In fact, I'm not even going to worry about my loan program anymore. I don't care about loans. I care about rounding to cents and I care about monthly payments now. So I'm going to go ahead and create a new file called financialutils_test.c. And what I'm going to do is I'm going to make it look kind of like my other programs here. Let me go ahead and just grab all of this right here. There we go. And financial utils tests. Let's move that over there. All right. And this is going to be on informal test suite for the financial utils library. There we go. All right. Let's go ahead and test this round to cents function. So I need a test case here. I'm going to go ahead and create a couple of variables here. X as my input. I'll just call it X because I don't have any decent other name. $123.45.5. There we go. Double expected output. Now I've switched to old school C here, but that's okay. The naming conventions, as long as you're consistent about it. I could go ahead and go input here instead. The expected output. If you were to call that function, what would be the expected output of rounding to the nearest cents here? 123.46. Okay. Let's go ahead and capture the actual output by calling the round to cents function on my input. Right? Now what I need to do is I need to check to see if the expected output and the actual output are the same. If the expected output is equal to the actual output, right? Then I'll say printf passed, right? And I'll end the line. If they are not equal, then I'll go ahead and output, what's the opposite of passed? Failed. There we go. All right. Now let's go ahead and compile all those things together. Remember that I've already compiled my financialutils.o file. So to compile this, it's going to be gcc financialutils tests, right, or tests, right? And then -lm to bring in the math library. Oops, sorry, what did I forget up here? I need to include the financial utils.h file. Great. Otherwise, that was just a warning, but of course it wouldn't actually compile in the end. Come on. Oh, since... Sorry, misspelled it. There we go. Oh, I can't believe I'm forgetting this. Financial utils.o. There we go. Remember that that's how you compile. You have to bring in the object file, then the test file, then the -ln flag. All right. Did it pass? Yep. All right. Good. Let's write another one. I don't want to erase this, right? Because that's a good test, right? So what I'll do is I'll copy and paste that and have another test down here. Except that I don't want this, I can't have the same variable names here. So what I can do is I can reset these variable names. Right? There, that's going to look much better. Give me a different test case. Let's make it, I don't know, like 55 and 1/3 cent. Is that an appropriate test case? I mean, it's a very large test case. That will hold in a double, by the way. Right? It's way bigger than 2.147 billion. That's the limit of an integer. That's not the limit of a double. Right? But this probably has more than 17 digits of accuracy here. Right? How many is that? Oh, it doesn't have a column. It's not listing the columns. Okay, I'm not going to be able to do it, but whatever. Let's go ahead and cut that down to $123 and 55 and a third 0.3 cents. What would be your expected output now? If it rounded it to the nearest cent, 55. All right. Let's see if we can break this. Nope, 2 of them passed. Okay. I bet I can try to. I bet I can get it to fail by going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and I'm going to try to break this here. Oh, and then what should this be? Still 55. Run that, and it's still passing. Darn it. I'm going to have to come up with a number that it won't pass because of that issue of 17 digits of accuracy. Right? The point that I'm trying to get across is that if these are floating point numbers, you're going to be introducing floating point errors. I don't want to use equals equals for doubles and floating point numbers like this. That's okay for integers. In fact, that's how you should do it for integers. But instead, what I want to do is I want to say, well, if it's close enough, right? If expected output and actual output are within, say, 0.001, right, then we want to pass it. Okay. So first of all, let's go ahead and put this into a variable, double. And I'm going to call it something that is descriptive of it. It's called a tolerance. That's your tolerance for error. Okay, you do this all the time if you're taking calculus right now, right? What does it mean for for a function to converge on a value? It gets close enough, right? It gets within delta or epsilon of the actual value that it converges to, right? And so this is our close enough value, right? So tests on doubles will pass if they are within our tolerance. ... All right. That gives me a variable to work with. Right? So how do I translate this if the expected output and the actual output are within that tolerance? How could I translate that into actual code? Yeah. Okay. If the absolute value is less than or equal to, right, we can, what about that border case? You can strictly less than or equal to the tolerance, right? Great. If the absolute value of the difference, because the difference could be positive or negative. We don't want to say that it's less than or greater than that thing. We want to know is the difference between them. And so we need an absolute value here. Is that how I write an absolute value in C, though? No. What is it? Okay. So here's one way of doing it. Abs, but that's not the correct way. Fabs. Why? It's a floating point number, right? These are doubles. If it's abs, it's for integers. and it'll get rid of whatever floating point value you have. So all the answers would be within like 0.1 or 0.9 or something like that. That's not what we want, right? So that is a much better way of dealing with floating point numbers. And I'm going to go ahead and update that one, and update that one. Okay. Oops. Get rid of that. There we go. So GCC everything together. And everything is still passing. Oh, no. Failed now. Okay, good. That's because this is way too big. That's what I was searching for. So this is way too big to actually represent. So let's go ahead and kick this down to 567. 567. Right. And note what I did here with 3 different test cases. I tested one where it would round up. I tested one where it would round down. Right. What about what else should I test? What? It's exact, right? So I should not expect any differences here at all, right? So GCC this, and let's see if they all pass now. Oh, it still failed. Why? Oh, I erased the actual line. There we go. That was the problem. There we go. Round to cents. I erased that line. Sorry. Now they should all pass. Yay, they all pass. Now I'm going to do this 3 times, 4 times, 5 times, 10 times or something, right? I want to report. I don't want to sit there and say, okay, 1 pass, or let's go with this one. 1 passed, 2 passed, 1 failed. I don't want to do all that manual work. So what I can do is come up here and start counting the number of tests that have passed and the number of tests that have failed. Int num passed. Right. Always initialize your variables. Int num failed. Always initialize your variables. And in addition to outputting passed, I can say num passed plus plus. If it failed, num failed plus plus. Okay? And let me just grab this entire thing. And you'll see a lot of repeated code here. And you'll be asking yourself, well, wait a second, why can't we do this in a function of some sort? And you're absolutely right. But I'm not even going to do that. I'm going to instead jump to the conclusion and let a library do all this work for me. That's in week 7, I think it is, or week 6. Week 6, that's it, after the exam. All we're doing right now is an informal unit testing to get the idea of how it works. Right? Now that I've got a total, let's go ahead and print that out. Printf. Num passed, number of tests passed, %d, and the line. And that's num passed. Number of tests failed. Right. Num failed. And let's go ahead and give ourselves a grade. Right. So what else would you want to know? Percentage passed. Right. What should we be looking at there? All of them should pass, right? Hopefully. And so what percentage should we be looking at? 100%. So I want the num passed divided by the num passed plus the num failed, because that's the total number of tests, right? Careful. Integer truncation, double. There we go. And I want a percentage there. Oh, 1%. Darn it. Times 100. There we go. 1%. No, there we go. Now we've got 100%. And note here, this is probably covered in Zybooks. How do you actually get the percentage sign? You go %. Right? There's the start of my unit testing, right? And this is great because now it's repeatable. Suppose that I go back over here to my financial utils and I make a change. I realize, oh, I don't need to divide by 100.0 anymore. I'll go ahead and change that. Recompile it, and now that I've got this test suite, I can go ahead and rerun that without doing any more work. Did I break anything so that now something is failing instead of passing? Hopefully I didn't break anything, right? But maybe I did. Maybe I copy-pasted and I screwed that up, right? We aren't testing that function yet, but we will eventually. Right? So this is your first informal unit testing, which you saw actually with the leap year exercise in Lab 3. We provided all this for you. We're going to provide more informal unit tests and then more formal unit tests by using an actual library to do all the work for us. This is a lot of boilerplate. Why should I have to keep track of the number passed and number failed? Why should I have to designate I do have to designate an input and output and the expected output, but why should I have to do this boilerplate stuff here of checking the answer and saying failed or passed? Right? Instead, I'm going to let a library do all that for me. And the library that we'll be using in a few weeks is called CMACA. But otherwise, that's where we'll pick it up on Monday. Remember, no class on Friday.